Okay, so today we're going to zoom in just enough to get into physics and then get back out of it, and it's particle physics at that, which is well outside my wheelhouse. But most of this is just a reminder anyway of what you learned in chemistry and physics and even from middle school. So again, this is just part two of wanting to make sure we're talking the same and that we understand what's happening at the most fundamental levels in biology. So you can understand atoms in one of two ways. Of course, there are protons and neutrons in the middle, and then you have electrons outside, either in an orbit cloud or in an orbit shell or an energy ring. And the reason that's kind of said this way is because electrons are so small and move so fast that it's understood that you can't determine their position and their speed or velocity at the same time. You can get one or the other, but not both at the same time. So it's not like watching a speeding car go past you on the highway. You can do one or the other. That's just the nature of particle physics. So here's a joke. Let's see a proton and an electron are sitting in the bar drinking, and a neutron comes in and says, "How much for a drink?" And he says, the bartender says to the neutron, "For you, no charge." Yeah, that's a dad joke, so that's free. All right. An element's properties depend on the structure of its atoms, and that's kind of no duh. You know that. But we discussed about the position of electrons and the valence of electrons last time, whether or not their orbital shells, their energy rings, were empty or full. And so an atom, of course, is the smallest unit of matter that still retains these properties of reactivity, size, mass, stability, and that's what makes an element an element. Once you divide up the atomic level, then you no longer have that element. And so you probably remember from middle school as well as your chem and physics that there are subatomic particles that we deal with in biology barely if we talk about isotopes or ions. Once you change the protons, though, you've changed the actual element. So if you want to understand the difference between their importance, neutrons have to do with basically whether or not they're an isotope and do they weigh more or not, and they'll lose those over time. So we'll talk about carbon 14, 13, and 12. And then you have electrons, which have to do with the chemistry or the reactivity of the atom. But the protons are the things that if you alter, you've altered the element itself. So basically, neutrons and protons are the larger ones, and they form the size and mass of the atom itself, measured in daltons. Certainly in AP Bio, we will talk about daltons and specific numbers when it comes to daltons. But for now, just understand that the particles are so small that you can't talk about, you know, negative 0.000 something numbers of milligrams. It doesn't work that way. So you had to make up a new measurement called the Dalton um, to measure these things. And it's understood that electrons form a cloud because they spin so fast. And the cloud just basically refers to the probability of where they can be located and how fast they're moving. So these are just language terms, from particle physics that kind of intrude on our biology understanding. When it comes to identifying these things for convenience sake, you'll get the short script of an element. So there's sodium. The top number that you'll see often is the mass number, and that is the number of protons and neutrons. And so that's where carbon normally has 12 there, but we can talk about carbon 13 or 14 because they'll have some extra neutrons. Whereas the bottom number is the atomic number, and that refers to the number of protons inside the nucleus, and you should have the same number of electrons as the same number of protons. That's kind of the rule. It is amazing how this stuff is set up, because I'm not a chemist, but it's amazing that you have to have one rule that says you have to have the same number of protons as electrons. They have to balance each other out. But then you have another rule that says it's most stable if you have all your electrons filling up an orbital shell. So some atoms have the same number of protons and electrons that fit perfectly into their orbital shells, and they're the most stable. Some atoms have the same number of protons and electrons, but the electrons don't fill up all their orbital shells or all of a shell, and they're the most volatile, able to react. And so the rules of the game are astounding if you just sit and marvel at chemistry, because if it were not for these rules or the way things are arranged or set up, even mathematically, the ratio of these things, nothing would happen. No chemistry and certainly no biology. From middle school and early high school, you need to make sure you've got these terms straight when we talk about mass, density, and weight. And so mass is the amount of substance. Density is how closely packed these individual units are. And weight is the effect that gravity has on that object. So mass, density, and weight are all different things, but they're related due to the type of atom and how closely packed they are, if they aggregate, if they collect, and then what kind of forces are acting on them from larger objects, which is gravity and weight. So I like this cartoon. It's a little bit cheesy, but it helps keep it straight. Related to matter is, of course, energy. And energy is the ability to either do work or the capacity to cause change. And so we can talk about potential energy, which has to do with the location of a structure, its position, and then we can talk about what it can and can't do. At this level, we're talking about the location or position of the electrons in their valence shells. And so one of the things that we can do with electrons in these energy shells and these valence shells and these orbits is that we can heat them up. In chemistry, in sophomore life in chemistry, you can take sticks and you put them in compounds and you put them in the fire, and the fires will turn green or red or blue or purple or whatever it is. And that's because of a wavelength, of a frequency of light that you're seeing. And what we're doing is we take the compounds on the stick and we stick them in the fire, and the fire heats them up with thermal energy. And those electrons jump out to higher energy levels, but they can't stay there, so they fall back. But it's in the fire, so they jump out, then they fall back, they jump out, and they fall back. And that back and forth motion creates a wave of energy that our eyes pick up on, and we say purple or red, and we see the color. So you can make these electrons move, and then they naturally move back. If you ask me why, that's beyond my pay grade. How do they know where to go and where to stay? Why don't they fall in? These are the questions that I ask B. Misko, and I just have not been satisfied. So it's kind of a mystery in chemistry how this works, and you can talk to him more if you want. Another strange thing is the nuclei of atoms never touch. If they do, that is explosive, right? Early chemists, when they realized the amount of space inside of an atom, one guy in particular put tennis rackets on his feet because he was afraid to walk across the floor of his apartment and that he would fall through. He realized that most atoms are just empty space, and that freaked him out. You don't need to wear tennis rackets, but the fact that you can press your fingers together, the protons and the neutrons are not actually touching. The atoms are not actually touching. The force that you feel are those electrons that are trying to repel, like two magnets, right? But it's just so small that we can't perceive the separation. And so, as I said, the chemical nature of all elements depends on where their electrons are located, and that's what I'm trying to get home, get across to you, is that protons, neutrons never touch, nuclei never come in contact. Really, this all has to do with these electrons. And so you've seen this before, okay? So we're focusing continually on these outer shells, on the behavior of the electrons. That doesn't define what they are as an element, but it defines what they can do. And so one of the things they can do is form compounds. So go ahead and write this in your notes. A compound is a substance consisting of two or more elements, and I love this last part, in a fixed ratio. We talked about these emergent properties that come from that, and we've already talked about table salt. Water is the same thing. You take hydrogen, which is the fuel of the sun, and you take oxygen, a highly combustible gas. You put them together in a certain ratio, a 2-to-1 ratio, and you get liquid water that you pour on a fire to put it out. If you understood the nature of both of those elements, you would never put that on a fire. But if you put them together, it becomes the one thing that can extinguish a fire, which is really, really strange. So we've been cycling through this concept of emergent properties. And so, for example, you get 3D shapes, you get arrangements that allow for certain things to happen. So water has a very funny shape and a very particular angle between its hydrogens. And then we can talk about the linear shape of H2 and O2, and then the cool uh, different shapes that you can have with carbon to make fats and sugars and whatnot. So 3D shape matters. So here is water, and we've already discussed how the oxygen and hydrogens unequally share an electron as a covalent bond, but that angle between those two white hydrogens is 104.5. And if that angle were any smaller or any larger, water wouldn't work the way it does. And so it has a very particular 3D shape. Table salt forms crystals because of its 3D shape and how it shares its ionic bonds, and so it makes an alternating pattern. And so the weakest bond that we have not discussed yet was hydrogen bonding. So since hydrogen on that water up above loses its electron most of the time, the proton is exposed most of the time. Protons are positively charged, so one side of that water molecule, the side with the two hydrogens, those white dots there, one side of the water molecule is mostly positive most of the time, and another side is mostly negative most of the time, the big red one, because it has a lot of electrons in it. So that makes the water molecule like a little magnet. It's got a positive side and a negative side. It's polar. And because of that, the positive side of the water might be attracted to negative sides of other atoms, and so they're attracted to each other like weak little magnets. So water is a polar covalent molecule. These types of weak hydrogen bonds are common when you see geckos climbing up glass. They use a van der Waals reaction where the electrons in their skin are loosely attracted to the positive atoms in the glass, say. And so it's just that they have a lot of surface area on their foot and they're walking up the glass because of these weak electron attractions. They don't have suction cups. There's no slime that they use. It's all van der Waals, hydrogen bonding, weak bonding electron interactions. And when they want to stop walking up the glass, they just curl up their toes to lower the surface area to volume ratio. This is also how insects walk on top of water. Water has this attraction to itself, creating surface tension. And so water acts like a little magnet with other water molecules, and it creates a type of film or loose attraction that insects, because they're so small, they can take advantage of. Water is also a great, they call it a universal solvent, but it's also a great dissolver of all kinds of things like oxygen gas and CO2. And so plants will use this for photosynthesis, and you can actually see them dissolving oxygen in water because water is attracted to all sorts of things and helps dissolve them, share them, surround them, diffuse them. So that's what's happening here. So when we talk about the 3D shapes of some of these important molecules, there's your 104.5. And so if someone ever asks you, what's the secret of life on this planet? You just say 104.5. They won't know what you mean, but that is the angle of the hydrogens on the water molecule. And were it not for that specific angle, water would not have all the unique properties that it does, which we'll talk about later. But geometry is important for a number of other things, like making different types of structures using carbon. And that will be the subject of our next discussion when we talk about organic molecules